In this example, I wanted to give you some practice with how to find an object's tangential acceleration, how to find an object's angular displacement, then also a little discussion about the radial acceleration of an object. So the first item that we're going to find here is the object's tangential acceleration. The tangential acceleration is my acceleration that's caused by my angular acceleration, but not in an angular sense. We're looking in a linear sense. We have a relationship here that we can take a look at where the tangential acceleration is equal to the angular acceleration times the radius of the object. Since I know that the angular acceleration is the change in my angular velocity divided by time, I can use the velocities, the angular velocities given to me in this problem to figure out my angular acceleration, then just multiply that times r to get my tangential acceleration. So essentially all I'm going to do here is substitute in. I know that my final angular velocity is 400 radians per second. My initial angular velocity is 100 radians per second. I know that it's accelerating over a course of 3 seconds. This equation right here will just give us the angular acceleration. Then you take that, multiply by r, and that's how you're going to find your tangential acceleration. Key thing on here is I know that I have a 23 centimeter diameter object. So I know the radius is half of that. So the radius is going to be 11.5 centimeters or 0.115 meters. If I multiply this out, what I'll end up with is 11.5 meters per second squared. The tangential acceleration is linear, so your unit is meters per second squared, not radians per second squared. If I ask you just for the angular acceleration, that would just be 400 minus 100, so 300 radians per second divided by 3, so that'd be 100 radians per second squared. That would be your angular acceleration for this problem. For the angular displacement then, I do need that because I am going to have to use my 100 radians per second squared in order to figure out the displacement, since I know that delta theta equals omega naught t plus 1/2 alpha t squared. So I'll need both omega naught and alpha in this problem here to figure out the angular displacement. So what I need to do here is I'll just plug in what I have. Delta theta equals, my omega naught is my initial, so 100 radians per second times 3 seconds plus 1/2 times 100 radians per second squared times 3 seconds squared, and then I'm just going to multiply this out. So if I do that, I'm going to get 100 times 3 plus 0.5 times 100 times 3 squared, and I end up with 750 radians is my angular displacement for this object. The last thing that I want to take a look at is the change in the object's radial acceleration. This is a little bit different because the radial acceleration is dependent on the angular velocity. It's not dependent on the angular acceleration. So when I have the object spinning at a rate of 100 radians per second, I'm going to have a certain radial acceleration. When I have the object spinning at 400 radians per second, I'll have a different radial acceleration. I want to find the change in that radial acceleration. When I mean the radial acceleration, that's essentially my centripetal acceleration. So essentially what I'm doing here is I'm just taking v squared over r to find my radial acceleration. If you think back to one of the simplifications I did in the previous video, that's equal to omega squared times r. So at 100 radians per second, I know if I just plug this in, so it's 100 radians per second squared times the radius, which is 0.115 meters, that will give me my radial acceleration at that angular speed, and that's going to be 1,150 meters per second squared. When I go to my 400, it's going to be 400 radians per second squared times 0.115 meters. So if I just figure this out, so it's 400 squared times 0.115, I'll end up with 18,400 meters per second squared, which means the change in the radial acceleration. So delta AR is just equal to 18,400 minus 11,000 or 1,150. So it's going to be 17,250 meters per second squared. So that gives you the change in the object's radial acceleration. More times than not, what I'll do is I'll ask you to find the object's radial acceleration at a specific angular speed. You won't have to find that change too much, but I wanted to illustrate to you that the radial acceleration does change as the object's angular speed changes.